Hi folks, welcome to this 7th video on a crash course in counting. In this one we're looking at something called Pascal's triangle. So far we've looked at fundamental counting principle, factorial notation, permutations and combinations, and sneaky questions that might come up around those ideas. Pascal's triangle is not something that was originally discovered by Pascal. It was known to ancient Chinese mathematicians millennia before Pascal's time. But there's some neat things to investigate here. So we have formulas for combinations, like we know that NCR is n factorial over r factorial n minus r factorial. Okay. But you can imagine hundreds of years ago, like for big numbers, those are very difficult calculations to do. We're deferring to our calculator all the time. So one of the many questions that might crop up is, well, how are people going to organize or know these values a long time ago? And one thing you can do is to arrange the set of all combinations in a little pattern here. So 1C0, just take my word that these are the values you'll get on your calculator, but 1C0 is if you have one person, how many ways can you select 0 of them? Well, there's one way to do that. You can select no one. 1C1, if you have one person, how many ways can you select 1? There's one way to do that. 2C0, if you got 2 people, how many ways can you select no one? One way. 2C1, there are 2 ways to select one person if you have 2 people. And this will be 1. 3C0, there's one way that can happen. Or you could type this in. 3, choose 1. If you have 3 people, there's 3 ways you could choose one of them. There's 3 ways you could choose 2 of them, and so on. If I write this triangle out, or this pattern out, it looks like this. Okay? And there's some really nifty patterns in this. Now, I don't like to write the head on Pascal's triangle. There's a 1 here that would come from 0C0. I don't find it that helpful, so I like to start it here. It's up to you, though. But things you might notice are that the outer numbers are all 1, and every row is going to have one more member than the last. So you might notice that the diagonals are going 1, 2, 3. So probably this number is going to be 4. And same the other way. This number is going to be 4. The question is, what's going on with that middle number? And here's the deal. Every interior number is the sum of the 2 above it. So 1 plus 2 makes 3. So same thing here. 1 plus 3 made 4. 3 plus 1 made 4. 3 plus 3 makes 6. Okay. But this row also has meaning. It's the 4th row in this headless triangle. So the first term is going to be 4C0. And the next term is going to be 4C1. And this will be 4C2, and 4C3, and 4C4. Now, the number of actual patterns that come up in this triangle is absolutely mind-boggling. And like I mentioned, we often call it Pascal's triangle in kind of typical Eurocentric fashion. That's not to diminish the fact that Pascal himself was a real Renaissance man, made lots of contributions to mathematics, to science, to theology, to philosophy. So we can go ahead and write more of this triangle out. 1 plus 4 makes 5. 4 plus 6 makes 10. 6 plus 4 makes 10. 4 plus 1 makes 5. Okay. So even though he's not the first person to notice this triangle, there are connections that were made to probability that are going to be important that come from this triangle. And we can keep going. So the 5th row gives us all the 5 C's, starting with 5C0. The 6th row is going to give us all the 6 C's, and so on, starting with 6C0. So it'll have 1, 6, 15, 20, 15, 6, and 1. And we can do more, right? It's not that hard to generate these numbers. A lot easier than using the factorials. And you could get this and look at for patterns in it for hours and hours. If you're interested in a book around this, the book The Number Devil is just a fantastic, quirky little sort of children's book, but really neat jaunt through different areas of mathematics. So Pascal's triangle can be used to find different combinations really quickly. If we wanted to find 4C3, here's what we could do. We could say, go to the 4th row, this will be 4C0, and this will be 4C1 right here, and this will be 4C2, and this will be 4C3. It's actually the 4th member of that row, because we start at C0, but we can find it fairly easily. Okay, so 4 C3 is going to be this number here. It's going to be 4. How many different teams of 3 people could be made from a group of 5? Well, that would be 5C3. Oh, I can go to my 5C row, which would be right here. Maybe I'll pick a different color. 5C row is going to be here. And this would be 5C0, 5C1, 5C2, 5C3 would be this 10 right here. It's like a little combination calculator for you. Now here's where it gets wild. If you expand binomials, which looks like it has nothing to do with any of this counting stuff, a plus b would be, let's do this in blue, would be multiplied out just a plus b, or 1a plus 1b. A plus b all squared is a plus b times a plus b, right? Which would give you a squared plus 2ab plus b squared. And if I put coefficients in front of these, I have 1a squared plus 2ab plus 1b squared. A plus b all cubed would be a plus b times a plus b times a plus b. We already asserted that the first two of those would give you a squared plus 2ab plus b squared. And if you multiply this out, it's going to take you a while. But we'll get an a cubed. We'll get 2a squared b, a squared b. We'll get ab squared. And then we'll get a squared b. And we'll get 2ab squared. Just foiling this out, plus b cubed. And when I simplify that, here's what I'm going to get. I'm going to get a cubed plus 3a squared b plus 3a b squared plus b cubed. Okay. And the next one, just take my word for it. So this one goes to here. The next one, if you were to multiply it out, is going to give you a to the 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the 4. Now that doesn't look like much of a pattern, but if we go up here and look at this triangle, oh my gosh, well, let me just write out Pascal's triangle again. I don't have to memorize it, I just have to know they're all ones on the outside and interior numbers to the sum of the two above it. The coefficients here are the exact same as from Pascal's triangle. So Pascal's triangle, or combinations in effect, give us a quick way to expand a binomial. And it turns out that expanding binomials has a lot of applications in probability. And it's also a thing that we'll probably see a fair bit when we start getting into calculus and having to find limits with polynomials. So I'll leave you with one last thought on this. It turns out that if you make 70% of your free throws, say you're a basketball player, free throws, the expansion of a binomial like this, 0.3 plus 0.7 to the power of 5, will tell you the probability of making, one of the terms will tell you the probability of making 0, 1, 2, 3, 4, or 5 of your next free throws. Okay, through binomial probability. And you might say, well, hold on, we just use order of operations. I add those, 1 to the 5, it's just going to be 1. Yeah, of course, if you just want an answer, the answer is going to be 1. But if you look at the way it's distributed when you expand that binomial for each of its terms in using Pascal's triangle, you're going to find some connections to the probability of each of those possible outcomes. So I'm not going to go any further with that in this crash course in counting. Really, this video here is just to bridge the gap between counting and binomial expansion. At the end of this video set, I'm going to put my Chapter 11 review from Math 621B, which is all about counting. Some of it would be review if you've been through this crash course in counting, and some of it will carry you a little bit further in terms of binomial expansion and the like. I hope that this has been helpful. Good luck with the material, folks. I hope you're intrigued, and take care.